Now to the second part of the lecture, more on risk assessment. The key idea here is that only prospective probabilities are useful in assessing risks, right? We want to know things before they happen, not that given that something happened, um, what's the probability of something else in the past. So if A is the event of drinking water, we know that the probability of A given heroin use is 1. Does this make drinking water a gateway drug? Of course not, because the probability of heroin given A will not be only 0.10, the base rate in the population. So, final application, screening tests. You have been tested for some dreaded disease, call it D. So this is your second announcement on, what is it? Constructing table for a disease. So, next important point. You have been tested for some dreaded disease, call it D, and your doctor confirms that you have tested positive for the disease. How despondent should you be? Maybe there has been a mistake in the test results. How accurate is the test? So, this is our lycanthropy example. You find out that the test is 99% accurate. So, you probably are sick. So what does accurate mean, though, in statistical sense? So here's a table of results for 100,000 hypothetical persons. That means for every test result that is positive, there's going to be 99 people who are sick, and 999 people who are actually healthy, given a large population of people. So you have a negative result. It's very good that you're not. If your result is negative, it's very likely that you're not sick. So the negative test is pretty good, right? So this is a 99 out of 1. So 99% that you will be sick, and you actually are sick, given a positive result. So from this table, we can compute a number for things such as test accuracy. If you have the disease, what is the probability you test positive? This is referred to as the test sensitivity. It's 99 out of 100, so 99% accurate. It refers to the probability that you get a positive test result given that you're sick. If you don't have the disease, what is the probability that you test negative? And this is referred to as this test specificity. Yeah, that's a wordy word. Which is 98 out of 901 over 99,900, which is 0.99. So this has a 99% accuracy as well. So this refers to the probability that you get a negative result given that you're healthy. So if we go back to that, it's probability that you get a negative result given that you're healthy over this whole area. So the first one tests this cell, 99 over 100. The second one tests this cell, 98,901. So they want to know how good you are at predicting someone that is actually sick, and how good you are at predicting someone that's actually not sick. So those are the two components. And they're referred to as sensitivity and specificity. So the test accuracy is simply a combination, a weighted mean of these two, sensitivity and specificity. In this case, since both SE and SP is 99, the test is 99% accurate. So what question is next? You know you have a positive test result, but does that mean you are really sick? What you really want to know is that the probability that you're sick given that you received a positive result. So the probability that you're sick given that you get a positive result is 99 out of 1098, which is actually only 9%. Now you're confused. Now where does that come from? Right here. Probability, so simple probability that you're sick, well, probability that you're healthy given that you had a positive result. Wait, sorry, I did that wrong. Probability that you're sick given that you got a positive result. So it's actually this first cell out of this total cell. So there is a 91% false positive rate for this disease using the current technology. So there's 99% that you're sick, given that you're actually you get a positive, given that you get a positive result that you're sick. So it's a really weird conditional probability where it's 9%. So there's a 91% false positive rate for this disease using the current technology. That if you're given a positive result of the test, that you're actually healthy. So that's referred to as a false positive. So the chances are quite high that you don't actually have the disease after all, so about 9 in 10. And then there's a base rate idea. What is the prevalence rate in the population, and is it small? Well, obviously it's a much less. Most people are not sick. Refers to this. So about 100 people in 100,000 individuals. So the prevalence rate is really small. So that's what leads to this weird false positive that occurs because the actual rate of the disease is very low. So an application on this is the National Consensus Conference on Mammography, usefulness of this screening procedures for women of average risk for breast cancer with no family history. So data relevant for drawing conclusions, basically the risk of dying by age and risk of breast cancer and risk of dying per 100,000 women by age. So here is your risk index and your mortality index. The trend you can see is that it increases with age. So here's the screening test data. You have the sensitivity and the specificity and the prevalence rate by the two age groups across time period. So you can see here between 40 and 49, the accuracy of the test is lower than between 50 and 64. There's also a lower prevalence rate as well. So now you have, as you know, when with a lower prevalence rate, the likelihood of a false positive also increases. So here's the hypothetical results for 1,040 to 49-year-olds. We know the prevalence rate is 1.6, so we put that here, 1.6 of 1,016. Next, we place the results based on the known SE. Remember, SE, the sensitivity is this first square, so just 75% of 16. Then we know the SP, which is the second square. I mean, this diagonal square right here. So once you fill that in, you'll get the rest of this. And now you can complete the table with the positive and negative results, just summing across these rows. So next, you can complete the table with the total positive and negative test results, compute the probability of sick given a positive and the probability of healthy given a negative, and you get these results. So the probability that you're sick given that you have a positive is 12 out of the total, and the probability that you're healthy given that you get a negative is this one out of the total. So here are the results, and this is the ratio of a false to a true positive. So given that probably that the disease is benign, so the false, given that you have a positive diagnosis, over the other ratio, which equals to 24.83. Which I don't think you have to calculate it. Yeah, the solution's not on here. But let me make sure I think it's 994 divided by 33.1. No. Yeah, this is a different calculation than this. It's one of these guys. 0.03 over probability that you have the disease given that you're positive. I would think it's, yeah, there we go. 295 divided by 12. So it's referring to this first row. And the second one should refer to the second row. Does it? Oh, we didn't calculate it for 50 to 64. That it would be recreating the same table, um, which is good practice if you would like to do a work problem and see if you can get this result. Recreating this table with um, the details from this guy. So recreating that same table with these different rates will lead you to the comparison solution for this. So, yeah. So, to wrap up, other data on this issue: 8 randomized clinical trials involving the screening of 40 to 49-year-old women found no decrease in mortality within a 7-year follow-up of initial screening. They found a 16% decrease in mortality after 10 plus years of follow-up of an initial screening. So this is 40 to 49, so that's still under the age range of 50 to 64. Essentially, what did they do with this? When you consider the variation due to sampling using the 2 standard deviation rule, the percentage could be anywhere between 2 and 28% mortality. This translates to an average of extending the life of 5 in 10,000 women by using early screening, with a lower bound due to sampling of 0 and an upper bound of 10, so 0 to 10 of 10,000. It is unknown how long the life of 5 in 10,000 women would actually be extended. So based on this data, the National Consensus Conference concluded that regular yearly mammograms in the low-risk 40 to 49-year-old populations were not useful and should be discontinued. Yearly screening should only begin in 50-plus-year-old women only. So Congress overturned the recommendation of the NCC of mammography, suggested instead that it be between a woman and her doctor, the presumed expert in statistical probability. And yeah, so here are some more information on that. Why are women under 50 not invited for screening tests? Women under 50 are not offered routine screening. Mammograms seem not to be as effective in premenopausal women, possibly because the density of breast tissue makes it more difficult to detect problems, and also because the incidence of breast cancer is low. The average age of menopause in the UK is 50. As women go past the menopause, the glandular tissue in their breasts infoliates, and the breast tissue is increasingly made up of only fat. This is clearer on the mammogram and makes interpretation of the X-ray more reliable. Breast cancer is also far more common in postmenopausal women, and the risk continues to increase with rising age. Women can ask their GP, general practitioner, to refer them to a hospital breast clinic if they are concerned about a specific breast problem, or otherwise worried about the risk of breast cancer. This is not part of the NHS breast screening program, which uses a routine call and recall system to invite well women. However, the same techniques are used in both screening clinics and hospital breast clinics for diagnosing breast cancer, and many staff work in both settings. Does breast screening save lives? The program in the UK has screened more than 14 million women, and has detected over 80,000 cancers. Research published in the British Medical Journal in September 2000 demonstrates that the NHS breast screening program is saving at least 3,000 lives per year. The figure is set to rise to 1,250 by 2010. By 2010, the effect of the screening program, combined with improvements in treatment and other factors, including cohort effects, could result in up to halving of the breast cancer death rate in women aged 55 to 69 from that seen in 1990. The World Health Organization's International Agency for Research on Cancer concluded that the mammography screening for breast cancer reduces mortality. The IARC working group, comprising of 24 experts from 11 countries, evaluated all available evidence on breast screening and determined that there is a 35% reduction in mortality from breast cancer among screened women aged 50 to 69. This means that out of every 500 women screened, one life will be saved. There does not appear to be any benefit in screening average risk women under 50. So that was their conclusion. So the summary of this is statistics. The data often go against their established policy. Given the cost of screening millions of people for what happens to be no effect, what would you do? So this is relating to the UK having a better, more universal health plan than us. So to offer that free screening could increase the cost of healthcare. So that concludes the lecture. I hope that helps you become more comprehensive of what's expected of you on the final. Again, review the announcements and how to work out those problems. And as I mentioned on them, you should probably have them down and know how to apply them given a very similar problem.